Welcome to the research breakout session, Advanced Adaptive Intelligent Systems. This breakout session presents recent developments in the area of conversational interaction, human-robot interaction, and technology in healthcare, conducted in collaboration with different schools at KTH and Stockholm University. My name is Sanna Kuoppamäki. I'm Assistant Professor in Technology in Healthcare at the Department of Biomedical Engineering and Health Systems, KTH. I am one of the co-PI of the Advanced Adaptive Intelligent Systems and will chair the session. The presentation takes about 20 minutes. During the presentation, you are welcome to ask questions in the chat box. After the presentation, there is 10 minutes time for questions and answers. Advanced Adaptive Intelligent Systems is one of the collaborative research projects between different schools at KTH and Stockholm University. The project members are Yolanda Leite, Jonas Beskov, Joakim Gustafsson, and Christian Smith from the School of Electrical Engineering and Computer Science, KTH. Sanna Kuoppamäki from the School of Chemistry, Biotechnology and Health, KTH, and Donald Macmillan from the Department of Computer and System Sciences, Stockholm University. The purpose of the project is to develop novel methodologies and approaches for developing an adaptive technology demonstrator, a smart kitchen robot with the ability to adapt to unknown environments and situations. In addition, the project will develop decision-making modules in the form of integrating physical human-robot interactions with conversational technologies that can adapt to users' needs, expectations, context, and actions. Our team brings together expertise in the area of conversational interaction, including technology in healthcare, computer-supported cooperative work, and human-robot interaction. Each topic is conducted by an interdisciplinary team of engineers and social scientists, bringing cutting-edge expertise in both technical design and qualitative understanding of human interactions and adoption and use of socially assistive robots. We have successfully explored all the adults' home cooking and opportunities for conversational and embodied robots through observations and video data. We have also set up an intelligent augmentation lab where experiments involving robots and humans in various tasks are conducted. This space will be the nexus where the project team will iteratively and collaboratively develop the technology demonstrator, envisioned to be an intelligent kitchen assistant, continuously informed by the target group, that is the aging population. The project has 3 aims, each contextualized in the specific empirical context and target group, that is the aging population. First, we will develop novel methodologies for human-centered artificial intelligence and machine learning. This will be utilized in the development of adaptive agents that can understand humans' communicative behavior and task-related actions. The overall goal is to achieve implicit adaptation of intelligent systems to users' context, needs, and preferences. The main novel aspects of our projects are, first, the strong focus on user adaptation, which is a crucial aspect when dealing with real-world applications, but has not yet been extensively investigated. And second, involving several stakeholders, such as older adults and elderly care providers, in all steps of the development process. We strongly believe that only by understanding and analyzing users' behaviors, actions, and skills in real-world settings, we will be able to develop systems that will be adopted and improve the health and well-being of the elderly, that is our target population. The project envisions to develop an adaptive technology demonstrator, a smart kitchen robot with the ability to adapt to unknown environments and situations. We believe this will have great potential to support a specific user group, that is older adults aged 65 and over, in a particular domestic task, that is cooking a meal at home. This technology demonstrator is envisioned to be an intelligent kitchen assistant for independent living. Cooking can be considered an integral part of older adults' health and well-being. Aging is often accompanied by difficulties in manipulation with tools and ingredients, and choosing right ingredients for meal preparation. Technologies providing collaborative support that combine cognitive and physical assistance in the home environment are still very rare. They have mostly focused on step-by-step delivery of recipes or choosing them based on goals such as health, sustainability, or availability of ingredients. Our project contributes to the design of more integrated, holistic, and supportive technologies in this space, with the goal to support older adults to live in their homes longer. but all while supporting independence, confidence, and sociality. We envisioned to develop a prototype of a conversational system that could provide both operational and organizational assistance in the kitchen. This type of assistance could combine both instructional assistance for recipes to support healthy and sustainable nutrition, organizational assistance to support the workflow and timing of the cooking process, and physical manipulation in opening, closing, and switching items in the kitchen. The conversational assistance is expected to be used by both older adults and the caregiver, such as healthcare professional. To better understand older adults' needs and interest in the kitchen, we conducted a video study of older adults cooking at home without any assistive technologies. The purpose was to investigate the complexity of kitchen tasks and create design principles for such assistive technologies in the kitchen to ensure the acceptability of such devices. Next part of the session presents key findings from this project.
Cooking is an integral part of independent living. Technologies providing collaborative support that combine cognitive and physical assistance in the home environment are still very rare, with most being focused on step-by-step delivery of recipes, or choosing them based on goals such as health, sustainability, or availability of ingredients. Our paper contributes to the design of more integrated, holistic, and supportive technologies in this space, with the goal to support older adults to live in their homes longer, but all the while supporting independence, confidence, and sociality. Through detailed analysis of video recordings of older adults cooking without any assistive technologies, we show the complexities of kitchen tasks. We present design principles that can be embedded into future kitchen technologies to help ensure that they fit with the needs and practices of older adults, while achieving the goal of helping them age in place. We report findings from a qualitative study conducted among older adults, those 65 years and over, in their own home where they lived alone or with their spouse. The data consists of video recordings of participants cooking a meal, as well as interviews and informal conversations before and after the cooking session. Each recorded cooking session lasted approximately 60 minutes and was followed by a 30-minute interview. Participants were recruited through their prior participation in design workshops at the university and were asked to be prepared to make a meal of their own choice in their own kitchen. All participants cooked recipes they were familiar with and had prepared before. They were not asked to follow a formal recipe, however they were free to do so. The analysis of the video recordings was guided by the principles of visual content analysis. The aim here is to unpack practices which are in plain view, seen but unnoticed. While many actions in the kitchen, which is a familiar and intimate environment, are highly routinized, they're also shaped in specific ways according to the locale and the unexpected developments of the ongoing cooking task. The recordings are watched with an eye to the flow of actions, conflicts and interruptions in the cooking process. In order to focus on age-related opportunities, instances involving fluencies and disfluencies in action due to physical and cognitive changes were highlighted. In an iterative process over multiple sessions, we extracted and categorized the clips of these instances, settling with top-level categories of physical manipulations, including cutting and chopping and opening and closing, organization and coordination of tasks, including switching between tasks and monitoring ongoing ones, and reorchestration and reorganization, including inserting and reordering tasks in the overall cooking action. To protect the participants' privacy, as you can see, their faces have been blurred and pseudonyms have been used. Participants demonstrated and described fluencies and disfluencies in actions, ranging from opening packages, using knives, lifting tools, and reaching for items in cabinets. The difficulties they experienced could delay or interrupt the ongoing course of action, and while some were resulting from age-related physiological changes, such as lack of strength or joint pain, others were not. In this example clip, we see some of these issues and highlight the support that could be offered. Emily visibly struggles to chop an onion here, starting to chop in a vertical motion with the knife in her right hand, using her left hand to hold the onion chopping board, but soon starts to struggle. Her limited strength plays a considerable role. She stated that arthritis had made such actions increasingly difficult and painful, showing the effects of changing dexterity on the cooking task. Emily's difficulties to chop the onion can in part also be explained by the knife's apparent bluntness. She adjusts the hold of both the knife and onion and continues to chop using a sawing motion while leaning her upper body closer and over the counter, highlighting the opportunity to support tool choice and maintenance. As she then uses both hands to add pressure and control of the knife, we see the chopping board start to move, as does the onion itself. This points to a dexterity-related opportunity for physical intervention by providing support to secure and orient objects in the kitchen as they are being used. Another method of achieving her goal of diced onions could also be suggested, taking into account the temporal, local and physical constraints in which Emily is operating. In the paper, we trace multiple examples through to principles for designing both operational and organisational assistance. By operational assistance, we mean supporting the practicalities of food cooking and preparation, and for organisational assistance, we see support needed to coordinate, replan, time and secure a successful outcome, good food in good time. The aim is to ensure that technologies enhance independent living, and as such strengthen the user's skills and capabilities rather than automating actions. Systems can track position, maintenance and suitability of tools for tasks the user is undertaking. This should then be used to reinforce the user's skills and competencies by supporting their choice of approach. For example, suggesting the use of a single-purpose tool for chopping onions may be the most efficient for that particular subtask, but the finding, assembling, cleaning and storing should be taken into account, and systems should support the user in their choice to use a knife instead, but maybe guide them to a suitably sharpened and sized one. Due to the day-to-day variability of physical and cognitive abilities of all users, alternative methods for tasks should be available and routinely encouraged so that coping mechanisms are developed and practiced over a longer period of time. Moving from one task to another requires fitting in with the temporal aspects of the cooking process and the spatial layer of the kitchen itself, and the location of objects and tools within it, all of which keep changing as the different tasks progress. In supporting the organisation and coordination of cooking actions, technologies then present options and their consequences in a participatory manner, supporting rather than instructing. Having the capability to provide this supported planning and coordination also enables reassurance of the user and supporting them to reflect on the current progression of the tasks they are carrying out during their food preparation.
Building on the previous study for designing kitchen technologies for aging in place, we investigated the methods of interaction for a conversational agent in the kitchen. The study was based on Wizard of Oz methodology of users' conversational interaction with cooking videos. Study showed that in the common case of aligning two ongoing tasks physically and temporally to achieve a successful meal, participants tended towards content-based requests for the video control, asking the video to go back to the part with the dog, whereas when in a linear task, they were more likely to request temporal changes, such as repeat the last minute. The formulation of the content-based requests highlighted an interesting interaction challenge that is developing a shared context of understanding the ongoing cooking task. Users' understanding was built on the video instructions, but also on the visual content of the video and the current state of the ongoing cooking task in their kitchen. At the moment, most conversational agents rely on transcription of the video in understanding the process. Our current goal is to strike the balance between the technical challenges of including other modalities and the interactional challenges of guiding the user to a shared understanding of the object and concept that the system is able to understand. Our important goal is to explore how users can interact with the conversational user agent, such as Google Home or Amazon Alexa, to better fit with the complex reality of everyday kitchen activity. Currently, we are experimenting with understanding the user's gestures in the kitchen space and in detecting when and how the user looks towards the conversational agent. These types of interaction rely on visual sensors. These are, in a sense, cameras, but where the processes, images of the skins are detected and made unavailable to any internet-connected components. Instead, the sensor extracts the information on eye gaze or gestures and passes that only as coordinate data. Explaining that the lenses do not enable the system to store or transmit images of them is important to ensure users' trust. It is also important to ensure that users are able to reason about and adjust the technology and their behavior to fit the comfort levels. The design of these sensor units is being iterated to expose through both their shape and feedback and the range and fidelity of what the algorithm can detect. The initial prototypes have concave insets for the lens which match the camera's view. This enables users to understand and manage what is being exposed to the system. The surrounding ring of lights is also used to provide direct feedback when the system detects either gaze or gestures, exposing when data is being collected and processed. These interactions allow a number of improvements over standard conversational interaction methods. They allow greater certainty in if the user intended to interact with the device, additional information on the context and commands involving other objects or people in the kitchen space, and an understanding of the user's current focus of attention, allowing reminders or warnings to be muted when the user is already attending to the situation. In a study of robot-assisted physical handovers, we also investigated the possibilities and conditions for physical robot embodiment to provide assistance in practical and nonverbal communication. Data will be collected from a few thousand human handovers of different types, where the robot can provide direct physical assistance in handling different objects and tools in the kitchen. The study applies machine learning methods to extract relevant characteristics. This type of robot embodiment can be integrated with the conversational system. By doing this, it is expected to adapt to different users and situations while retaining characteristics from human actions. Sometimes robots can be perceived as frustrating by users. In a study of cognitive overload and robotic failure, we investigated frustration detection with thermal imaging. We created a dataset of 18 participants engaging in 2 frustrating situations due to cognitive overload and robotic failure. Both situations are common in human-robot interaction. The setup is shown on the left figure. Machine learning model has been trained to detect frustration by just using thermal regions of the interest with the accuracy of 87%. In addition to thermal imaging, other modalities such as RGB and physiological data were also collected for the sake of comparison to thermal imaging. The results of the experiments were the following. Using thermal regions of interest, it has been shown by the feature selector algorithm that the 3 main regions that are relevant for frustration detection are forehead, nose, and lower lip. Next part of the presentation presents adaptive speech and gesture generation, focusing on robotic mimicry and generating user adaptive speech and motions. The following video clip shows how the Furhat robot can adapt to user speech.
Hi.
In a study of robotic mimicry, we investigated how robots' face and neck motions can adapt to the users. Users' movements are analyzed in real time during the conversation. In this experiment, 12 participants participated in a task-based interactions, so-called survival task. 3 conditions are presented. 1, no movement, 2, non-adaptive movement, and 3, adaptive movement from the robot. Results were the following. Users commented favorably on the adaptive robot that they perceived to be more intelligent and more friendly, but users still trusted the non-movement robot more. No significant differences in this pilot study were found. In a study of generation user adaptive text, speech, and gestures, we collected a corpus of 6 hours of speech and motion capture of spontaneous monologues about persons' hobbies and daily activities. GPT-2 fine-tuned on the transcripts in order to generate text in line with the actor's interest and linguistic style. Extended Chatterton 2 trained on the multimodal corpus in order to generate speech and gestures that sound and look like the actors.
The thing is that like it's such an individual thing. Like, I don't know, like I was like, I wanted to write a love story.
Building on the insights and findings presented above, we envision the future work to focus on participatory design of physical and conversational interventions with older adults and their caregivers. These kind of interventions could be the so-called kitchen reminder, providing organizational assistance for timing of the cooking process. The system would create alerts every time the user needs to move from one task to another. Or it could be a tool handover, operational assistance for manipulation with tools and ingredients. The system would support in handling objects and tools in the kitchen. Here you can find some project publications. Thank you for listening. We are happy to answer any questions and comments regarding the presentation.